please welcome our next speaker, Dr. Yurong Chen.
Good afternoon, everyone. Today, it's my pleasure to introduce our research work to advance deep learning-based video understanding. So my talk will be more technical. So in this talk, I will first introduce our research motivation and the research program on video understanding at Intel Labs. Then I will introduce our research results, latest results on face analysis, emotion recognition, deep learning-based video recognition, and video pattern and multimodal analysis. Finally, I will summarize my talk. Nowadays, video sensing is everywhere, and cheaper, which results in video data exploring. The vast majority of data in cloud and on edge and devices is video. Cisco projects by 2019, there will be 5 million years of video content traversing the internet every month. And by then, video traffic will be 77% of all internet traffic. So definitely, the amount of video content will continue to grow. The key challenge here is how to process and understand this huge amount of video data. The only way is to use video understanding technology. Video understanding is one important part of computer vision. Basically, it's the process of analyzing and understanding images and videos. It's mainly focused on object processing, unlike pixel processing in the image process. Its objective is to derive knowledge out of images and videos of the real world. Here is some sample video understanding capabilities, such as face detection, face recognition, emotion recognition, text recognition, object classification and detection, activity recognition, scene understanding, video classification and summarization, and so on. Among them, video recognition, including object classification and detection, is the most basic task of video understanding. Classification is to predict the class of the main object of an image. And detection is to predict the class, not only the class of the object, but also the predictions with tight bounding boxes. So in the detection task, the objects can be of any size of any number. So detection is much more difficult than classification. Here is the example. For a given image, by classification, we know there are person and camera in the image. And by detection, we know not only the object classes, but also the positions with tight bounding boxes. By further analyzing the relation, we know this person is taking picture. This is action recognition, which is much more difficult than classification and detection. Deep learning is behind most of the recent breakthroughs in video recognition, speech recognition, and natural language processing. Here is a little history of 1,000 category object classification on ImageNet large-scale video recognition challenge. In 2012, a CNN-based method, AlexNet, it was handcraft feature-based methods, and it achieved 40% top 5 error improvement, which is a huge improvement. From then on, all submissions have been based on HoloNets, and it achieved about 30 to 40% improvements every year with deeper and deeper HoloNets. In 2015, ResNet from Microsoft achieved 3.57% top 5 error with 152 layers, which outperforms the human performance. In a Nature paper, deep learning pioneers Yurong Chen, Benjol, Hendon also mentions HoloNets allow the dominant approach for almost all recognition and detection tasks and approach human performance on some tasks. To address the video data explosion problem, we initiated a video understanding and synthesis research program across Intel labs. This program is mainly focused on research innovation in smart video data processing on Intel platforms. And one of our major focuses is video understanding. It includes not only almost all video understanding tasks, but also some fundamental components, such as Caption architecture, video odometry, SLAM, video indexing, and so on. Our lab, video cognitive computing lab, is mainly driving video understanding research at the Intel Lab China. We are mainly focused on research innovation in cutting-edge video cognition and machine learning technologies for smart computing to enable novel usage and user experience. We have 3 research projects for video recognition. The first is face analysis emotion recognition, which aims to develop an advanced engine for 2D, 3D face analysis and emotion recognition. This engine can be widely used in smart places, virtual reality, augmented reality, mixed reality, automated driving, and robotics. And the second project is deep learning-based video recognition. In this project, we are developing IPs for designing, training large and deep learning models for Intel hardware, software, video recognition, and understanding solution design. It includes research work on efficient algorithm design and DM model compression. And the third project is video pattern and multimodal analysis. Our goal is to collect dots of vision, speech, language, and knowledge, and machine learning to make machines be able to see and inference like human beings. Currently, we conduct research on image and video captioning and video question answering. Later, I will talk more detail on these projects. In the past few years, we developed a full face analysis pipeline with better-in-class algorithm to help differentiate Intel products. This pipeline is based on our own developed IPs for face detection tracking, facial landmark detection tracking, face recognition, face profile, gender at age recognition. Based on this leading face analysis technology, we collaborate with different BU to impact Intel hardware, software, application, and solutions. We also extended our face analysis research to emotion recognition, since emotion recognition is very important for smart computing and smart systems. In 2015, we invented the action unit aware features and interactions with multitask learning method to decode the facial muscle movements and their inherent interactions explicitly and densely. Based on this method, we developed a multimodal solution to win the emotion recognition in the wild challenge in Multimodal 2015 in the audio-video-based task. And the competitors included 74 teams across the world. The audio-video-based task is the main task of the Multimodal challenge, which uses some movie clips to mimic real usages. It's very challenging due to some bad lighting conditions, large head pose variations, and some occlusions. Here just to show you a snapshot of our real-time multimodal emotion recognition prototype. We can do the real-time face pre-processing and the facial impression recognition to get the video recognition results, and the real-time audio acoustic analysis to get the audio recognition results. After fusing these two modalities, we get the final emotion recognition result. Last year, we also developed a deep learning-based solution, which is very efficient, HoloNet. And it elaborately combines several state-of-the-art CERN backbones, including concatenated residual structure, inception residual structure, which are by design naturally complementary to each other when handling emotion recognition tasks on untrained conditions. By fusing several modalities, we achieved accuracy about 58%, ranked the second out of 100 teams in the Emotivo 2016 challenge. And our paper on HoloNet was chosen as the most influential paper in the past 4 years Emotivo challenge by the program committee. Since our method is a low deep, then we are using actual data for training, and its speed is hundreds of times faster than the other competitors. As mentioned previously, face object detection is the basic task of visual understanding. And the traditional method is handcrafted feature-based sliding window methods, and which is very time-consuming, and its accuracy is very low. Then deep learning triggered breakthrough in classification, which translated to significant improvements in detection as well. Current top deep learning-based object detection solution can be divided into two families. The first family is region-based methods, which use region proposal to reduce the searching space of objects, and use a region-wise subnetwork to classify and refine region proposal to get final detection results. This family includes the famous ARSEN SPP, fast ARSEN, our invented HyperNet, RFSEN, and so on. This method can achieve very high accuracies, but the speed they are relatively slow. And the other solution family is region-free methods, including YOLO and SSD. This method treats object detection as a single shot problem, straight from image pixels from the bounding box coordinates by fully convolutional networks. This method, their major advantage is highly time efficiency, and but the accuracy is not the best. Based on the success of the two solution families, we invented our own solution to associate the best of both methodologies and eliminate the major demerits. So next, I will introduce HyperNet and our own to you. HyperNet is a unified framework for region proposal generation and object detection. It's the first much-scale, scene-based object detection solutions. It's based on a discriminative and compact hyperfeature map, which flexibly integrates low-level edge, mid-level part, and high-level shape abstract convolutional feature maps into one uniform space. Thus, we can directly scan across the entire image in one single run. The hyperfeature map is shared by two small networks for region proposal generation and object detection. Compared to the famous ARSEN solutions, it has two advantages. First, it has high recall with less number of region proposals, which means we can use much less region proposal to achieve high detection accuracy. Second, detection is much more efficient, both in space and time. Our means reverse collection pyramids with object supply networks, which is the object detection framework to associate the merits of region-based and region-free methods and eliminate the major demerits. Under fully convolutional architecture, it resolves the two fundamental problems. First is multi-scale object localization with reverse collection pyramids, which enables the network to detect objects on multi-levels of scenes. Second is efficient lective space mining with objective supply networks to significantly reduce the searching space of the objects. The objective supply maps could explicitly reflect the existence of an object, and the object with various skills will respond at the corresponding feature maps. Until RN can achieve leading performance, both in accuracy and speed. And this work will be published in this year's CVPR. We tested our than the famous Pascal VOC 2007-12 and MSQQ datasets, and it achieved the best single model accuracy when we submit the paper. Specifically, with VGG16 as pre-trained model, it achieves 81.3% mean AP on Pascal VOC 2007 and 80.7 mean AP on Pascal VOC 2012 datasets. And its superiority increases when datasets become larger and more difficult, as demonstrated by the results on the MSQQ dataset. With about 1 gigabyte memory requirement at test fit, it can run in real time at 30 frames per second, which is 5 times faster than the fast ASM method and our invented HyperNet speed-up version. It can detect different objects in complex scenes, in video analytics and automated driving usages. Deep learning-based methods can achieve high accuracies, but they are both compute and memory intensive due to tens of millions of parameters. To improve deep learning efficiency, besides the efficient network design, another way is model compression. In this direction, we develop a leading and elegant solution, low-bit deep compression, which can achieve 100-level lossless compression on DNNs with low precision weights and low precision activations. Thus, it can pave the way for efficient deep learning inference, both for hardware and software. Our solution includes 3 key modules: DNS, dynamic network surgery, to seek optimal DN architecture; INQ, incremental network quantization, to constrain optimal DN with low bit weights; and VLE, variable length encoding, to constrain optimal DN with low bit activations. Next, I will talk more details on the INQ. INQ is a lossless low-precision DN quantization method, which can approximate full precision DN models with the version. Whose parameters are restricted to either the integer powers of 2 or 0 with fixed bit width. For example, 4-bit, 3-bit, 2-bit, even 1-bit, to represent the range of the wall parameters. It will resolve the network quantization accuracy loss issue by proposing 3 level operations: parameter partitioning with a well-defined metric, group-wise quantization and retraining, and making the whole progress as an incremental network quantization and accuracy enhancement procedure. To the best of our knowledge, INQ is the first lossless network quantization solutions, thanks to the 3 level operations. Besides without loss of accuracy, it's model-free, which means it has no assumption of the network architectures, and we can use it in any neural networks, not only in RN, but also CN, but also RN, LSTM, and other neural networks. And we also achieved high training efficiency. And this work was just published in this year's ICLR conference. Next, I will show you some results. We conducted extensive experiments on the ImageNet classification task using almost well-known deep CNN architectures to well testify the efficacy of our INQ on different CNN architectures. Specifically, at 5-bit quantization, with AlexNet, VGG16, GoogleNet, ResNet 18, and 15, our quantized model have consistently improved accuracy compared to the 32-bit floating point references. Taking ResNet 18 as an example, our quantized model with 4-bit, 3-bit, and 2-bit weights also have improved with similar accuracy against its full precision baseline. And as for the 2-bit quantization models, although its top 1 and top 5 recognition rates is a little bit worse than the pre-trained full precision model, but its accuracy is considerably much better than the state-of-the-art results reported for the binary weight networks and the ternary weight networks. Combining DNS, INQ, and VLE, we developed low-bit deep compression solution for lossless model compression. We tested on the Alex Lab model. The state-of-the-art solution, deep compression solution, achieved 35 times compression by combining network pooling, vector quantization, and Huffman coding. And our solution can achieve 71 times compression without loss of accuracy, which is at least 1 times better than the deep compression solution. With 2-bit weights and 4-bit activations, we can achieve up to 142 times compression with just a little bit drop of accuracy. And this work lays a solid foundation for the deep learning acceleration on the edge, mobile, and embedded devices. It can speed up the deep learning inference by tens and hundreds of times. For video pattern and multimodal analysis, we focused on a more novel and challenging viewing task, dense video captioning, which aims to describe a video clip with informative and multiple informative and device captioning sentences. We invented a weakly supervised dense video captioning method with rolling video level sentence annotation during training procedure. This is why we call it a weakly supervised solution. Here I will show you sample examples. Here is the video.
Winkelmeyers told their kids this doesn't happen often. Seeing the champion on a tour, even less likely.
It's a once-in-a-lifetime chance.
For this video, we can generate segment-based description. For example, a woman in red blouse is taking picture of children for the first segment, and a group of people are taking pictures of a horse for the second segment, and kids are being interviewed for the third segment. Another pattern in a short video clip is rich description of regions. Here is an example. Our solution can generate multiple informative and device video regions sequence, and we can generate, our language model can generate captioning sentence for each sequence. For example, for the first region sequence, we generate a man is drinking from a cup, and for the second region sequence, we generate a man is drinking from a bottle. And for the third region sequence, we generate a man in a suit is talking to another man in a suit. Our solution not only produces dense caption, it also achieves outperforms the state-of-the-art single video captioning methods with a large margin, as shown by the results on the MSR VTT dataset. Next, I will show you video caption demo. So you can see the video caption we generated on the bottom of the video. So here, we just show some dense video in some video segment, not every segment. Actually, we can generate the 5 sentences for each video sequence. It's interesting. Here, a man is talking. Then we see the screen. We say a man is giving a presentation. And when we see the audience, we give a man gives a presentation in front of a group of people. So the result looks great, but I think it's still far away from achieving human-level performance. But we believe vision plus other modalities, such as speech, language, and knowledge, is the right way to go to bridge the gap from video recognition to understanding. So, in summary, we are addressing video data processing, video data exploring problem by research innovation in video data, smart video data processing on Intel platforms. And we're conducting cutting-edge computer vision and machine learning research to advance deep learning-based video understanding to help differentiate Intel products. And that's all. Thank you for your attention.